Trapezoids and kites. What we're going to be looking at here are two other quadrilaterals that are not parallelograms. They do not carry the properties that parallelograms carry. They have their own unique properties, and we're just going to take a look at those. A trapezoid is a quadrilateral with exactly one pair of parallel sides. All right, typically when we think of a trapezoid, we think of what is called the isosceles trapezoid, which we'll look at in just a bit here. That will be when the legs are congruent to each other. But by definition, a trapezoid is a quadrilateral, four-sided figure with exactly one pair of parallel sides. Okay, so if I want to draw a picture of one, what I could do is just take something like a ruler that has a straight edge on the top and the bottom. I could just trace those. And then what I can do is go ahead and just connect the sides that we have here. And you're gonna notice when I connect them, because I didn't measure out the top and the bottom and I didn't try to adjust them so that they were sort of like balanced or symmetric with each other, all I really wanted was to make sure that the lines are parallel. This fits the definition of a trapezoid. You have exactly one pair of sides that are parallel to each other. The others, how they look, that's just how they can be. So they don't need to be the same size. They don't need to be at the same angle. That again, we'll be getting into our isosceles trapezoid. So that will fit our definition. In addition to that picture, I want to draw one other one. And this is going to be called a right trapezoid. It's actually a pretty common figure. It's not really the one that you might think of. So it'll probably work out better if I start it right at the edge there. Because what I want to do is create a right angle on one side. I'll go over these lines here in a second. Okay, so by copying the edges of the ruler, I do fit the definition of a trapezoid. But in addition to that, what I was aiming to do here was to create some right angles that I have there, and this would be called a right trapezoid. So this in general is just a trapezoid. This would be a right trapezoid. Just because you do have a right angle in there. All right, so the one that we're normally gonna think about when you hear trapezoid is gonna be the isosceles trapezoid, and that will be that symmetric looking one. Okay, so it's gonna be closer to this picture than here, but this side would lean in a little bit further so that it would match up exactly to that. The legs would be congruent. The two sides that are not the parallel sides, those are referred to as the legs. Okay, so let's see if we can get a picture of an isosceles trapezoid. Since my measurements on the opposite sides are weird, I'm gonna have to probably just estimate some things here. I'm gonna make the top 6 centimeters. That's probably longer than it needs to be, but what I want to do is know where my middle is, so then I can maybe flip this over and, man, that's gonna be hard to do. All right, the 3, three looks like it's pretty close to underneath, like right at the middle. All right, so for that one, it's gonna look really long. Okay, that'll be fine. I think that's gonna get me that symmetric look. With the units on the opposite sides being different, that's a little bit hard to do. Okay, I think I got it there. A little bit of eyeballing. The top and the bottom definitely parallel because I traced the ruler. What makes this isosceles, is that these two leg lengths will be congruent to each other. It does end up having a symmetric look, and what we're gonna do in just a moment here is prove that the base angles are gonna be congruent. The base angles would refer to this and this. These are going to be congruent to each other. We'll show in just a moment. These are also considered base angles, okay? Those are going to be congruent to each other. So in the isosceles trapezoid, here's everything labeled. You've got the congruent legs, you've got the congruent base angles at the bottom, you got the congruent base angles up at the top. And one thing I forgot to mention as well, the parallel sides in any of these pictures are referred to as the bases. So you actually have two bases for your trapezoids. All right, so here's the proof that I was referring to. We have an isosceles trapezoid, top and bottom are parallel, the leg lengths are going to be congruent, and we're going to prove that the base angles are congruent. In particular here, what I'm going to do is prove that the bottom two angles are congruent. Technically, I should also prove that the top two angles are congruent, However, once these are shown to be congruent, you can easily determine that these would be congruent as well. You could possibly use consecutive interior angles to show that these would be supplements to each other. These would be supplements to each other, meaning they both add to 180. If these two are equal to each other, then those two are going to have to equal to each other to also have 180. So that part I'm actually going to leave out and just focus the attention on the bottom two angles. That would be down here. All right, to start things off, let's go ahead and give it a name. I'm going to have to refer to some things here. Let's call it TRAP for trapezoid. And our given information is that TP, that leg length here, is going to be congruent to RA. That is our given because this is an isosceles trapezoid. You could even refer to that as the definition of an isosceles trapezoid. I'll just say that it's given because it's actually mentioned in the prompt part there. All right, the trick to this one is to add in a couple of lines, okay? What we are going to do is draw a segment, let's see what I want to call it. Let's call it TX. We're going to draw TX. So I'm going to be using T and then introducing a new one called X. And I'm going to draw it so that draw TX perpendicular to PA. Okay, I'm going to draw TX perpendicular to PA. All right, so that means that right here, I'm going to create a right angle, which is really building a right triangle to look at. In addition to that, so in the same step, what I'm going to do is I'm going to draw another one. We're going to draw R, let's call it RY. Make that one perpendicular to PA as well. Okay, so that's going to be here. Call that Y. Okay, so a couple auxiliary lines that we added into the picture. All right, so why did I do that? Well, if you look at the picture, the two triangles that are built on the side here, if this whole thing really is symmetric, and I think we can see that it is, these are going to be congruent to each other. Okay, now we can't just make the claim that they're congruent to each other. We need some sort of a shortcut that's going to apply this. And so far, all we know is that PT is congruent to RA, and that at angle X, we got a right angle, and an angle Y, we got a right angle. So we do have two pieces there, right? We've got an angle, we've also got a side length here. But what's special in this case is that the angle is a right angle, okay? And this isn't just any side, that's called the hypotenuse. That's there. So if we can say that either these leg lengths are congruent or these leg lengths are congruent, that'd be PX and YA, or the verticals there, we can actually use hypotenuse leg. And we are going to be able to do that. For 3, we're going to be able to make the claim that TX is congruent to RY. Okay, and the reason for that, because we're measuring at the same angle between those parallel lines, because we're using the same angle, not just that it's a right angle, but because we're using the same angle, we can say that the distance between parallel lines is constant. That's a weird one, but it's true. It's a true fact, and we know it. It's almost part of the definition of parallel lines. For them to be parallel lines, the distance between them needs to stay constant. Okay, so if those are congruent, if we used like side angle side type stuff here, you would end up with side angle, which is not one of our shortcuts, right? That one's not one of our shortcuts. You could use two sides if you had an included angle. Not what we have here. But there's that one case that if the angle is a right angle, you can use hypotenuse leg. So that's the one that we're going to use. Basically, hypotenuse leg, if you have a right triangle and the hypotenuse and the leg here is the same as the hypotenuse and the leg here, you could technically do Pythagorean theorem if you had the numbers and figure out that PX would be the same thing as AY, and that would give you side. So that's really where that stems from. Okay, but we're going to go ahead and just say here that triangle let's go around that way. TPX is congruent to RAY. That's triangle ray. They're going to be congruent, and I ran into that space, but it's hypotenuse leg. That's the shortcut that we're going to use. So, what was it that we're trying to prove from the very beginning here? That the base angles down here, P and A, we want to prove that they're congruent, and they are. They are. Angle P is congruent to angle A by CPCTC. And there you are. Your base angles are congruent. And going back to the beginning, as I mentioned, we should also prove that the top angles are congruent. Okay, I'm going to leave that out because it'll make it longer, right? And I think that this really gets to the main point of how we can at least conclude that two of them are congruent. The follow-up is really just, in fact, you got different ways of working with this. The one that I mentioned before is that angle R and A are consecutive interior angles, so they got to add to 180. Same thing over here. Well, if P and A are the same, these have to be the same. It's a logical approach, and you can just write up some equations and do a little bit of algebra and show that they have to be congruent to each other. You could also identify that the top skinny angle up here would need to be the same as that one by CPCTC. These would be right angles right there because we drew it as a perpendicular, and that would just be maybe AIA or corresponding angles, whichever. You could take your pick at it since it's perpendicular, and then show that the sum of those plus the sum of those would be the same. For our other shape here, a kite, as you can see here, all I really have is a definition. Don't really have anything else but a piece of patty paper. The definition of a kite is a quadrilateral with two pairs of consecutive congruent sides. Okay, they're going to have two pairs of congruent sides, but those sides are going to be consecutive. That means back to back, not across from each other. And as a kite, you're going to really be looking at like that classic cartoon kite that you see Charlie Brown flying around in the air. So how do we build a picture of this and make sure that it actually connects? Okay, we need two pairs of consecutive congruent sides. What I'm going to do is just start with two sides that are not congruent to each other. Put them back to back. See, I can probably draw this a little bit larger. All right, so that has a length of about, what would that be, about 2 inches. Doesn't really matter, but I want to make sure that the other one's different here. And you know what? I'm going to need to make my picture a little bit smaller. Okay, I'll just flip it upside down in a minute. All right, so I got two sides here that are different lengths. What I need to have is consecutive congruent sides. So whatever the length of this is, I need that over here, and whatever the length of this is, I need that over there, and I need them to connect together to make the figure, okay? So if I measure and then try and like angle it out here, it's a real big like guess and check game, and we don't want to do that. So instead, what we'll do is fold this over onto itself. All right, and when I do that, I'm gonna make the crease like right at the endpoints. That's what I'm aiming for here. Let's see if I got them. All right, looks like they're pretty good there. Oh, what am I gonna trace, right? All right, I'm gonna flip it over, trace the other side. Oh, you know what, that's actually gonna be on the back side of it. No, you can see it, that's fine. What I should really do is flip this around, fold it backwards so that pencil size are on both ends, or both sides of it. We'll get there. All right, I think that's right. Except this pencil likes to leave marks behind. All right, so by definition, two congruent consecutive pairs of sides, two pairs of consecutive congruent sides. These are gonna be congruent. I literally copied them, right? These are gonna be congruent, and that fits the definition of a kite. All right, so let's go ahead and start with a little bit of vocabulary that we have here. The angles that we've got, if you have it positioned like this, call that the top, call that the bottom, okay, just for simplicity here. Those angles, the top angle and the bottom angle, are called vertex angles. Those are called vertex angles, both of them. All right, now as you look at the picture, you should ask yourself, are the vertex angles congruent? And I hope the answer to that would be no, that they're not. Up here, where you got the shorter sides, the angle created is going to look a little bit larger, okay, than what we have here. Now, inductively, I could actually verify that by just attempting to fold over and seeing that, oh, these don't match up to each other. Okay, so vertex angles, those are not going to be congruent to each other. In fact, if they ended up being congruent to each other, that would end up meaning that you don't actually have a kite, you would actually have a rhombus when it would all be created. So these will never be congruent to each other. The other pairs of angles though, right? Remember that those are actually made as copies of each other. I can fold that over again. So they're a perfect match to each other there. Those angles are in fact going to be congruent. They are referred to as the non-vertex angles. Not a very clever name. Non-vertex angles. Okay, that'd be that one, and then there's the one over there. Not sure if I want to label that spot. These are in fact going to be congruent. The vertex angles are not congruent. All right, and that can actually be easily proven, not just because of how I folded it using inductive reasoning, but if I drew a diagonal here, I drew that long diagonal there, you could use the reflexive property to show that the left and the right triangles are congruent to each other, okay? So if these sides are congruent, you'd end up with side, side, side. Those triangles would be congruent. The corresponding parts of those triangles, which would be the non-vertex angles, would be congruent to each other, and you could easily write up a proof for that. All right, in addition to that though, right, when I drew this here, not only is it that the non-vertex angles are going to be congruent, but even the angles that are up top here, those two will end up being congruent with each other, right? Corresponding parts of congruent triangles, still based off of that side, 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 and even down here. These would be congruent. Now, these are going to have different markings than the ones that are up at the top because they're not all the same, okay? But we can also conclude this, that if we draw a diagonal, that long diagonal here from vertex angle to vertex angle, it does in fact bisect the vertex angles. That is true. All right, what happens if we draw another diagonal though, right? What happens if we draw this one? Does that bisect the non-vertex angles? Does it do that? Well, if we fold over onto that, so at least inductively, if I fold over on that diagonal, you're gonna notice the angles are not matching up here. So that'll be a no. These are not gonna be congruent. All right, so we get this neat thing here that's almost kind of weird and contradictory. The non-vertex angles are congruent with each other, but the diagonal that goes through them does not bisect the angles. You don't get that property. Yet, the vertex angles, who are not congruent to each other, are bisected by the diagonal that goes from one to the other. Okay, so it's like you get one thing or the other with these. All right, and then there's one more property that we get to look at, which is what happens right here with both of those diagonals. You do get a perpendicular in that spot. You do get a perpendicular there. And we can prove that it is perpendicular by looking at the top two triangles here. Okay, just the top two. By definition, that side and that side are congruent with each other. You've got the bisected angles we would have proven from the CP-CTC earlier. You also have a reflexive property from that point up to the vertex angle, which means you've got side angle side. Okay, so if they're congruent, these two angles need to be congruent. The only way that's possible is if they are perpendicular, because they're also a linear pair, right? All right, so then we get that piece. And in addition to that, if we keep going and talking about these two triangles, this right here, see, I don't think I've used triple markings yet. All right, this and that would be corresponding parts, so they're congruent as well. So when you got both of the diagonals drawn, you get a perpendicular, and that short one, the one that goes from the non-vertex to the other non-vertex, those would be congruent to each other as well. All right, so overall, in a kite, it has tons of properties, and there's a lot of things that we can do with this. You've got congruent sides, you've got some congruent triangles in different places, you got angles being bisected, you've got a perpendicular. There's really a lot of things that we could do with this.
Wait, there was.